Good evening to all. This session is continuation of tutorial 1. In the last session, we were able to complete 4 problems of tutorial 1. However, the 3 problems are pending. So let us now take up problem number 5. Okay. So I hope this problem is now visible on your screen. So if we read the problem, we are having a 5 meter high and 8 meter long and 0.22 meter thick wall whose representative cross section is given in the figure. So on the bottom right corner of this slide, we are having one figure. So we can see that this 8 meter is actually one dimension of this one, and one dimension is actually 5 meter high. Okay. And we have the thickness is given as 0.22 meters. Now, if we see, so cross section is given over here. Now, what we are having, if we see the cross section of this wall, so we are not having homogeneous material over here. So if you see, this first strip is made up of material A, then in between we are having actually 3 different strips, where middle strip is made up of material B and top and bottom strips are made up of material C, and then we are having this D, E and F as different like materials which are layered together. Okay, so over here this wall is not having homogeneous composition. Yeah, within individual material like A throughout is homogeneous, which is having thermal conductivity equivalent to that of F, which is equal to 2. Then Kb is 8, Kc is 20, Kd is 15 and Ke is 35. Okay, so these are the individual thermal conductivity values given, and their values are in watt per meter degree Celsius. Okay, and then left and right surfaces of the wall are maintained at uniform temperature of 300 and 100 degrees Celsius respectively. So left side is 300 and right side is actually 100. So even this is marked with the help of arrows also over here. We have to assume that heat transfer through the wall is one dimensional. So you can see this Q arrow which represents the transfer of heat. It is in a single direction from left to right. Okay. Now based on this information, we have to determine the rate of heat transfer through the wall. So how much heat is transferring? What is the value of Q dot? And we have to also determine the temperature at the point where B, D and E meet. So you can see this is my B material, this is D and this is E. So this particular where my pointer is now located, this particular location is actually the intersection of B, D and E. So we have to determine temperature at this particular junction. Okay. And we have to also determine the temperature drop across the F. So you can see this particular face is actually left side and right side of F. So we have to determine that within this F, between the two faces of F, how much we are having actually drop of temperature. Okay. So we are already having the sketch known for this particular problem, and I hope you all have gone through the lecture where concept of thermal resistances is discussed, because for solving this particular problem we have to employ the concept of thermal resistance. Okay, can you tell me what is the formula of thermal resistance for the case of conduction heat transfer when we are having a plain wall? What is the formula? Can you tell me?
L by K.
L by K.
L by Ka, where K is thermal conductivity of the material, A is area, and this particular area will be actually in a direction normal to that of direction of the heat transfer vector, and then this L represents the thickness of the wall. Okay. Now, looking into this schematic diagram, can you tell me how our thermal resistance circuit will be looking like? So let me first mark the 2 extreme node points. So one is this node where we are having temperature of 300 degrees Celsius, and another, say in the right side, extreme right, I have one node point with temperature of 100 degrees Celsius. Now in between, depending upon the configuration of this composite wall, what we have to do, we have to actually determine the thermal resistance circuit. Can you tell me how it will be looking like? One by one, tell me. From left, if I start resistance, I will be having initially I will be having, can I draw one resistance something like this? So
Yes, sir.
This is nothing but resistance of A. Okay, so what is A material we are having? Its thermal resistance we have included. After A, what will be happening to the circuit?
So 3 in parallel, CBN.
Yes, 3 in parallel. So here 2 are actually C and C1, C2 I can mark it, and 1 is B. Okay, so let me mark this as resistance B. Then I have one resistance over here, and this is nothing but my RC1, and one resistance I have over here. This will be RC2. Okay, then after that, after this, we will be having D and E2 in parallel. Okay, so let me write these two as well. So one is RD and another is RE. Okay, so this is one. Then after this, I have a single material throughout the entire area, which is in the normal direction to that of heat transfer. So that's why I'll be having simple resistance as RF. Okay. Now, can you tell me what will be value of RA? So for RA, if you see, the thickness of this portion is nothing but 1 centimeter. Okay, so I can write L as 0.01 divided by Ka. K is how much? K of A is nothing but 2 watt per meter degree Celsius. So divided by 2 times A. How much is area? So if you see, this is actually 5 meter high and it is 8 meter wide. So our area, which is normal to the direction of heat flux vector, will be nothing but 8 multiplied by 5. So that is my area, 8 by 5. And as it is the case of a plane wall, so every time we will be having area as nothing but 8 by 5 only. Okay, this point is clear?
Yes, sir.
Okay, so now based on this, I can calculate the value of RA. Can you find out similarly the values for RC1, RB, RC2, etc.? Can you find out values for all resistances?
Yes, sir.
Okay, so I will not go into now detailing of this because this is very simple. The way I have calculated resistance for A, similarly you have to calculate resistances. Let me take up one case for RC1, RB and RC2 just to show that how the effect of area will be actually coming into picture. Okay, so can you tell me what change will happen? What change will happen over here? Whenever I will be calculating,
area will be divided.
Yes, area will be divided because here you can see total is, so this is 4 centimeter, 4 and 4 only. Okay, I think this statement seems to be having some issue because if you see here individual heights are marked. So based on the individual heights, it seems that this total height of this domain is nothing but 12 centimeter only. Okay, so please make this change in the statement over here. I think this is some issue. So based on the figure, if we see, we are having total height as nothing but equal to 12 centimeters. This point is clear?
Yes. But sir, we can also have like a repetition of the same structure up to 5 meter high.
Yeah, you can do, but this is not the case actually. Over here, whatever figure is giving, this is the entire plane wall. Okay, so probably this is some issue with the statement from the source from where I have taken this problem. Okay, so all of you, while you are solving this problem, please adhere to the dimensions which are given over this figure. Okay, this point is clear?
Yes.
Now, if I have to calculate RC1, RC1 will be equal to what is this dimension? This thickness is 5 centimeter. So I can simply write 0.05 divided by what is the thermal conductivity of material C. The thermal conductivity of material C is 20. So I can write 20, and what will be area? Area will be this C for the top portion RC1, which I am considering. It is 4 centimeter high, and in third dimension, if I take 8 meters, then it will become 8 multiplied by 0.4 only. Okay, sorry, 0.04 only. So that will be my area. Similarly, if I have to calculate RB, can you tell me what will be the value of RB?
2.05 upon 8.04.
Okay, so KB is 8 here. 8 into 0.04. Okay, so this way I can calculate all my resistances. Once all the resistances are known, what I have to do, this circuit I have to further convert into 3 resistances only. So what will be the resultant of these 3? Can you tell me the resultant of all these 3? RC1, RB, and RC2?
1 by R is resultant equal to 1 by R1 plus 1 by R2 R square, because
Yes. So let me consider the resultant of these 3 is as RR1. So I can write 1 by RR1 as nothing but 1 divided by RC1 plus 1 divided by RB plus 1 divided by RC2. Similarly, if I consider the resultant of RD and RE as RR2, that will be becoming 1 divided by RR2 equal to 1 divided by RD plus 1 divided by RE. So once I have these equivalent resistances available for these two, then I can simply convert this circuit into RA, and here I can simply write now R1, and here I can write R2. So if I do so, I can now easily calculate my total resistance. So what will be the total of these 3?
There is some.
Yes, it will be addition, because now resistances are in series. So this will be my final equivalent circuit with R total. Here I have 100 degrees Celsius, and I can say that R total will be equal to RA plus RR1 plus RR2. Okay. Now, what is the first part of the question? If you see, the first part of the question is the rate of heat transfer through the wall. Can you tell me what will be the rate of heat transfer through wall?
Excuse me, sir.
Yes.
Sir, there is one more resistance RF in series.
Oh, sorry. Yes, I missed it over here. Yeah. So here I will be having one more RF over here. Yes. So here I will be having plus RF also over here. Okay. Now can you tell me what will be heat transfer? Rate of heat transfer?
Delta T by R2.
Q will be equal to delta T divided by R total. Okay. So this is from our analogy to that of electric circuit. So delta T is given as 300 minus 100, and R total we will be calculating, and the value of R total you should get about 0.349 degrees Celsius per watt, and if you substitute this value, you will be finding finally the rate of heat transfer to be 572 watt. Okay. One more correction you do. dimension whatever is given as 8 meter, please consider it as unit only, 1 meter only. Okay, so whatever answers I have uploaded for this particular question, these are by considering the height to be 12 centimeter and this width dimension to be equal to 1 meter. Okay, so this is some issue with the question from the source from where I have taken it. So basically this width has to be 1 meter and this height has to be 12 centimeter. Okay, so please note down these corrections. Now can you tell me how to determine part B? What is part B? We have to determine the temperature at the point where sections B, D and E meet. So can you tell me how to determine this temperature? Any one of you?
First, we calculate the resistance between A and E, and then we apply Q is equal to delta T by R, and Q is known, so we can find out the final temperature at the
Yes, correct.
junction.
Correct. So what we have to do now, if you see our circuit, we know the value of temperature at this point, and we want to calculate the temperature at the junction of B, D and E. So if you see, the junction of B, D and E is this point. This particular point is the junction of B, D and E. Let me consider that temperature at this point is, say, T. If T is the temperature at this point, now whatever heat is transferring through this portion in between the gradient of 300 minus T, that has to be equal to the total heat transferring through the entire circuit, because then only we will be having steady state situation. Okay, so by doing so, I can write that my heat transfer will be equal to 300 minus T divided by this resistance in between the two terminals which I am considering over here. Okay, so by doing so, I can write that Q will be equal to 300 minus T, which is the temperature of the junction and which we have to determine, and divided by what we have to do? Divided by, we have to do this RA and R1, because these are the two resistances which are coming into picture. So total will become RA plus R1. So these two values are known to us. So if these two values are known to us, I can easily, and this I have already calculated in the previous part, so I can easily determine the value of T. So if I calculate, if I substitute all the known values, I'll be finding final temperature to be 263 degrees Celsius at the junction. So is this part clear, or anyone is having any confusion?
So can you show the problem statement again?
Okay. So problem statement says we have to determine the temperature at the point where the sections B, D and E meet.
Sir, the intersection of B, D and E means that one point, right?
Yes.
So the temperature of that point would be the same as the across the cross section of that point.
Yes, because we are considering the concept of one-dimensional heat transfer. So when we are saying we are having one-dimensional heat transfer, it means gradient of temperature only exists along the x direction. We don't have any gradient in z and y direction. So that's why along the entire cross section we will be having same temperature. Arjun, is this point clear?
Right. Oh, yes, sir.
Okay. So anyone else is having any other confusion? Otherwise, we'll move to part C. So if we go to part C, here we are having that we have to determine the temperature drop across the section F. So this is very simple. Can you tell me what will be temperature drop across section F?
So similarly, we can find the temperature at the cross section of D, E, and F and subtract them. It's simplest.
Yes, it is very simple actually. So if you see here, we are mainly interested in delta T across F. So this is very simple. I can simply write Q to be equal to delta T across F divided by resistance of F. Now I know resistance of F, I know Q. So from here, delta T of F will comes out to be 143 degrees Celsius. Okay, so this is very simple one. Now one important point which I have forgot, or I have not read the statement fully. We have to disregard any contact resistance at the interfaces. So I am sure, and I have seen, I think in the lecture number 7 or 6, you are introduced to the concept of contact resistance also. So over here we are considering that when we are having this composite wall, the different materials are having perfect contact between each other, and there is no air gap, because of which contact resistance is including. If in case of this, if we are having contact resistance available, what changes we will be finding? Can you tell me? Say if I have any contact resistance in between these boundaries in the interfaces, then what changes will happen? Say I have this contact resistance in between D, E and F, some from D to F and some from E to F. What changes will happen?
But then we'll have to take 4 resistance in parallel.
Yes.
One is both for, one is direct and one is for gap for both cases.
Can you tell me what is the formulation of this contact resistance? What is the formula? R contact.
R gap plus R contact.
Okay. What is the value of R gap? How to calculate R gap? Contact is very simple, L by Ka only. But how to find out R gap?
1 by H radiation है.
Not H radiation. H radiation will depend if we are having radiative heat transfer. There may be some other heat transfer, yeah, but altogether 1 by HA, where this H will be applicable for the gap reason. Okay? Fine.
Yes.
Okay. Now let me take up. So all of you are requested to go through one question, at least one question, where the concept of contact resistance is also involved. Okay, so please practice a question of contact resistance also from your textbook. Now let me take up this problem number 6. So if we read this problem, we are having a firefighter's protective clothing referred to as turnout coat, and is typically constructed as an ensemble of 3 layers separated by air gaps as shown schematically. So can you see this schematic diagram? Here, this entire represents nothing but the protective clothing of a firefighter, and here we are having 3 layers which are separated by air gaps. So you can see this is first layer, which is called as cell, having thermal conductivity Ks and thickness Ls. Then we are having 1 millimeter air gap over here, and then second layer is actually moisture barrier having conductivity Kmb and thickness Lmb. Then another 1 mm air gap we are having, and then we have a thermal liner over here having thermal conductivity KTL and thickness LTL. Okay, so this is actually our fire side. This cell will be exposed to fire, and this is actually the firefighter's body side. Okay, now if we see the thermal conductivity and the thickness dimensions are given over here in this table. So for cell, we have thickness of 0.8 and thermal conductivity of 0.047. Similarly, other values are also given. Now, it is mentioned that the air gap between the layers are 1 mm thick, and heat is transferred by conduction and radiation exchange through the stagnant air. So wherever we are having air gap, there we will be having actually transfer of heat by 2 phenomena, conduction and radiation. Okay, so the linearized radiation coefficient for a gap may be approximated as. So what is the meaning of linearized radiation coefficient? I think it is already dealt in the lecture. So all of you know about this term, H
Yes, sir.
radiation.
Yes, sir.
Okay, so if we expand actually radiation heat transfer, it comes out to be T1 plus T2 into T1 square plus T2 square, and this entire is approximated with the help of 4 sigma into T average cube, where T average represents the average temperature of the surfaces comprising the gap, and the radiation flux across the gap may be expressed as Q radiation equal to H radiation into T1 minus T2. Okay, so radiation heat transfer we can determine by this relation. So nothing but we are writing this expression of radiation heat transfer equivalent to that of convective heat transfer equation, and we are having this coefficient which is given over here. Okay, first thing we have to do is we have to represent the turnout code by thermal circuit, labeling all the thermal resistances, and then we have to calculate and tabulate the thermal resistance per unit area, like meter square Kelvin per watt for each of the layers. So remember one thing, whenever we are calculating the thermal resistances, we are calculating on unit area basis. So wherever we are having value of A, that we have to substitute equal to 1. Okay, and we have to also estimate the conduction and radiation processes. So we have to find out the resistances for all the phenomena. Okay, and we have to assume that value of T average is 470 Kelvin, and it may be used to approximate the radiation resistance of both the gaps. We have to comment on relative magnitude of the resistances. So let us first solve only first part. Can you tell me what will be the equivalent resistance circuit? For problem number 6, say this is my fire side, and this one is say firefighter side. So if I bring you back to the schematic, from the fire side we have first a cell of Ks conductivity and Ls thickness. Now can you tell me what will be the resistance circuit? In the cell, how many resistances we will be having?
Only one.
Only one, because cell is an opaque material. So here we will not be having radiation heat transfer. So that's why within the cell we will be having only say R conduction in cell. Okay, then after that we have a gap of air. So in the gap of air, how many resistances we will be having?
2, one for radiation and one for conduction.
Yes. So let me write here R gap radiation, then I will be having one R gap conduction, because through air both conduction and radiation phenomenon will be happening. Then we have moisture barrier. Once again, moisture barrier is some opaque material. So over here, what I will be having? I will be having only one resistance, R conduction and moisture barrier. After this, what we will be having after this? Once again, two resistances, because we have gap. So R gap radiation, I am using same symbols because this thickness and properties are actually same. And then after this, I will be having R conduction through the thermal liner. Okay. So now what we have to do? We have to determine the value of all these resistances. Can you tell me what will be conduction through cell? What will be the value? Cell thickness is 0.8 mm. So I will be having 0.008 divided by conductivity of the cell is 0.047. 0.047 multiplied by area, I have to take unit. Okay. Now, can you tell me what will be R gap radiation? Please tell me the value for R gap radiation. What is the formulation of radiation resistance?
1 upon HA.
1 upon H radiation into A. Okay. So now if you see, we have value of H radiation equal to 4 sigma into T average cube, and T average we have to assume a value of 470 Kelvin. So my H radiation will become 4 into, what is the value of sigma? Have I written correctly?
Yes, sir.
Okay. So if you do calculate this, you will be finding that, okay, I don't have noted the value of H radiation. So let me keep it like this only. So this will be, once H radiation is obtained, I can find out the gap radiation resistance. Now what I have to determine? I have to determine gap conduction resistance. So what will be gap conduction resistance? L gap divided by K of air into A. Okay. So K of air from our property table corresponding to 470 Kelvin, I can determine the conductivity of air. Okay. So this is one additional task, because if you see, nowhere thermal conductivity of air is mentioned in this problem. So if thermal conductivity of air is not mentioned, what we have to do? We are having some property charts available in our textbook. So from that property chart, corresponding to 470 Kelvin average temperature, we have to determine the thermal conductivity of air. Is this point clear?
Yes, sir.
Okay. So I think now all of you can easily determine the value of all the resistances. Let me give you the final table over here. So first, let me write our let me write for cell, then I have gap, then I have this moisture barrier, then I have once again gap, and then I have a thermal liner. Okay. So here let me write conduction, and then let me write radiation resistance. Okay. So if I see in the cell, I'll be not having any radiation resistance. Here also I will not having, here also I will not having. So for cell, if I see conduction radiation will come out to be 0.01702. For gap, conduction radiation will come 0.0259. For barrier, it will come 0.04583. And for gap, it will be same as calculated earlier, because gap is having identical characteristics. And then for this, it is coming out to be 0.00921. Okay. Now let me talk about radiation resistances of the gap. So it will be 0.04264. So once again, it will be same. Okay. Now, can you tell me how to find out the overall resistance? How to find out overall resistance? So between these two, we have to use parallel formulation. Once these two parallel are calculated, so their equivalent you will be finding. So equivalent gap resistance I am writing over here. The equivalent of these two will be based on the parallel formulation as 0.01611. Okay. So this is the equivalent resistance if you apply parallel formulation. And if I have to find out total resistance, what will be its value? Can you tell me what will be R total? Please tell me R total.
Sum of all.
It will be this plus this plus this plus this and this one. Okay, so from here gap we have to consider the final resistance. So this total resistance will come out to be 0.1043, and the unit is meter square Kelvin per watt. Okay, now in terms of calculating the relative magnitude, we can see that radiation resistance is actually one order less in comparison to, we can see that the thermal resistance of this thermal liner is actually one order less in comparison to all the order of other resistance values. Okay, so this is how you can like compare the relative value of all the resistances. So first part is okay to everyone? Shall I move ahead to next part?
Sir, what is the basic requirement of thermal liner in like what does it role it display?
Yeah, so basically if you see, the thermal liner will be having some properties which will be actually like it will be providing this type of system so that it is comfortable with our body actually. Okay, so there is some human body we are having. Okay, so if we are having some hard material in between, so that may not be very comfortable to the body, and ultimate aim is like what we want to do, we want to avoid any maximum heat transfer. So our major idea is to have this coat in such a fashion so that our thermal resistance is actually increasing and this firefighter is feeling as less heat as possible. Okay. Then we have next as part B. So if I read part B, it is having, we have to for a pre-flash over fire environment in which firefighter often work, we have to determine the typical radiant heat flux on the fire side of the turnout coat. Okay, it is given as 0.25 watt per centimeter square. We have to determine what is the outer surface temperature of the turnout coat if the inner surface temperature is 66 degrees Celsius, a condition that would result in burnout injury. So 66 degree is towards the firefighter side, and we have to determine the temperature of other side and the heat flux which is coming from the fire on this fire side of the turnout coat. It is 0.25 watt per centimeter square. Okay. So can you tell me how to find this? How we can determine this value? Please tell me how to determine this value of heat flux.
So Q is equal to delta T by R, and Q is known.
Q is not?
Q is known and R is also known. So we
Okay. Q is known to us. Yes. So in that case, tell me the values. Heat flux is 0.25. What is heat flux?
0.25.
Unit is watt per centimeter square. Okay. So I have to do 10 to power minus 4 over here in order to find out in watt per meter square. And temperature, say fire side is T and another temperature is given as 66, and our resistance I have just now calculated as 0.1043. Okay, so from here if you calculate, temperature will comes out to be 327 degrees Celsius on the fire side. Okay, so this is one practical example of thermal resistance analogy. Moreover, the previous problem which we have discussed, that is also related to the design of insulation wall for our different materials, where we put some composite wall arrangement, or say when we are having our household building, there also the wall of a room will be having different layers. Some layer of plaster, some gap through windows, somewhere glass. So all these things are nothing but makes our walls as composite walls, where we can employ the concept of this thermal resistance in order to find out the heat transfer, heat loss, or heat gain through that particular medium. Okay. Now the question of variable thermal conductivity is problem number 4, which I have already told you in the previous lecture, because variable thermal conductivity is also one important concept. Oh, sorry, not variable thermal conductivity, conduction with heat generation. Okay, so many of the times what happens, whatever the problems we have solved now, here within the medium we were not having any generation of the heat. Okay, many times this may happen that whatever surface we are having, where we are actually studying the rate of heat transfer, within that surface also we may have some volumetric generation of the heat. Okay, so if we have volumetric generation of the heat, how to solve that particular problem, that I have discussed in problem number 4 already in our previous lecture, previous session. Now today we will be talking about one special problem where we will try to see that if we are having variable thermal conductivity, how to include its effect into our consideration for numerical solving. Okay, so this problem 7 is like a nuclear reactor is shielded by larger brick walls, and it is desired that liquid metal coolant pipe can be through a portion of the wall as far from the reactor as possible to prevent radioactive contamination, but at a specified temperature level so that the coolant will not freeze and stop the flow. So it means we are having some wall, and in that we have to pass some coolant pipe that should be away from the nuclear reactor side. However, it should not be so far that temperature is dropping below the freezing temperature of the fluid. Okay, and wall is having 80 centimeter thickness, and brick follows a thermal conductivity curve specified by K equal to K naught times 1 plus alpha T, where K naught is 0.22 and alpha, so this is a typo over here, this value of 0.002 is actually for alpha, so please note it down, alpha equal to 0.002. The brick surface towards the shield is at 600 degrees Celsius and outside face temperature is 40 degrees Celsius. The pipe is located where the temperature in the shield has fallen to 320 degrees Celsius. We have to determine first assuming mean K and second by considering variable K, that this statement is once again incomplete. So okay, it is complete. We have to determine the pipe location by considering first the concept of mean thermal conductivity and second time by considering the concept of variable thermal conductivity. Okay, so can you tell me how to approach for the solution of this problem? First, we have to draw the sketch of the problem, because then only we will be able to understand. So we have a wall, okay, brick wall, and its thickness is 80 centimeter, and one side of the brick wall is maintained at temperature of, so reactor side is maintained at temperature of 600 and other side is maintained at 40 degrees Celsius. So say this is my reactor side. Okay, it is at temperature of 600 degrees Celsius and atmospheric side is at 40 degrees Celsius. Now it is given in the question that through this brick wall somewhere we want to pass a pipe of the coolant. So let us consider this is nothing but a coolant pipe. Now two conditions are given, that coolant pipe should be as far as possible from the reactor side so that there should not be any radioactive entry into the coolant. Okay, and another important thing is, if we will be removing this pipe too far, so its temperature, this pipe will be located in the low temperature region, so it should not go in such a situation that the coolant within the pipe is freezing. So because of that, it is given in the question that we have to locate pipe where temperature in the sealed has fallen to 320 degrees Celsius. So it means we have to locate it corresponding to temperature of 320 degrees Celsius. Okay, so now we have to determine this location X, say from this end it is X. We have to determine the value of X first by considering the concept of mean thermal conductivity, and second by using the actual expression of variable thermal conductivity into our heat transfer analysis. So this problem statement is clear, whatever I have explained over here?
Yes, sir. I have a small doubt. In what case can the coolant freeze in this case, sir?
If temperature goes below its melting temperature.
Okay, so we are using anything else than water here, right?
Yes, or it may be that yes, probably we are using some coolant which is other than water. Okay. Okay, so let us first use the concept of mean conductivity. Can you tell me, if we are having the relation of conductivity given as K equal to K naught into 1 plus alpha T, how to determine mean thermal conductivity? How to determine mean conductivity?
Integration of K dt divided by integration of dt.
Yes.
Yes. So basically, I have to integrate this K over dt, and my limits of temperature are, say, this is T1, this is T2. So limits of temperature are from T2 to T1. If I am integrating over temperature, I have to also divide it with the temperature difference delta T, which is T1 minus T2. Okay. So all the values are given. K naught is given as 0.22 and alpha is given as 0.002. Okay. So if I substitute over here and integrate, let me substitute once. I'll be putting over here K naught into 1 plus alpha T. So it will be becoming K naught times T plus K naught alpha into T square by 2 and limits from T2 to T1. Okay. So if you calculate the value of conductivity, it will come out to be 0.353 watt per meter Kelvin. Okay. Now I know the value of conductivity. Can you tell me, if I know the mean conductivity, how to determine this location of X? Any one of you?
I think first we need to calculate the resistance, and by using L by K formula, and then Q.
So we will assume that the mean conductivity is it's the uniform conductivity of the whole material.
Yes. So initially we will be assuming that mean conductivity is uniform conductivity, and whatever is the heat transfer in this section, say this is my intermediate point. So whatever is rate of heat transfer in this section, same will be rate of heat transfer in the remaining section under the steady state assumption. Okay. So I can find out heat transfer in this section and equate that to heat transfer in the right section. Okay. So heat transfer in the left section will be, we know heat transfer rate is equal to delta T by R. So delta T in the first section is nothing but 600 minus 320, and R is L by Ka. So L we don't know. We are only knowing that in the first section we have X as the thickness. So X divided by conductivity mean I have already calculated, and area, let us assume 1 meter square unit area. Okay. And this heat transfer will be equal to heat transfer in the remaining portion under the steady state assumption. So I can write it to be 320 minus 40 divided by, can you tell me what will be resistance? What will be resistance?
80 minus X.
Yes, it will be 80 minus X divided by Km into A. So from here, can we determine value of X? So if we calculate x, it will comes out to be 40 centimeters. So this is using the approach 1. Now we have to use approach 2 of variable conductivity inclusion in heat transfer. Okay, so to do so, what we have to do? I know heat transfer is equal to minus k into dt by dx. Okay, and k is k naught into 1 plus alpha t into dt by dx. Let me take dx to the left hand side, so I can write q dx equal to minus k naught into 1 plus alpha t into dt. Now if I want to calculate this q, not only dx but for this entire left portion, so what I can do? I can do integration of q dx within the limit 0 to x. Okay, because from here we are considering x equal to 0 at this point, and at this location we are considering it is some arbitrary location x. Okay, so integration from 0 to x, and here I will be having integration in the right side. I have to integrate along the temperature, so my limits of integration will be in terms of temperature. Can you tell me what will be limits of integration? What will be limits of integration?
600 to 320.
Yes, it will be 600 to 320. Okay, so this is the heat transfer on first part, equation number 1. Then what will be heat transfer on other part? Q into dx from x to L, say L is total length, and that will be equal to integration of minus k naught into 1 plus alpha alpha t into dt, and this integration will be from
320 to 40.
320 to 40. Now this, can I equate the left hand side of, I can say that left hand side of both the equations will be same. Can I say this thing? Under the steady state condition, our heat transfer will be actually same. Okay, so because of that, I can equate this right hand side of both, and from here I will be able to calculate the, sorry, I cannot equate because I am calculating, integrating it over the dx portion, so that portion thickness is different. But what I can do from here, if you see, I can find out the value of right hand side for both the equations, and from left hand side actually I will be finding this formulation in terms of x and L minus x. So by doing this formulation, I can equate 1 and 2, and from these, by jointly solving these two, I will be finding value of x to be 47 centimeter. This point is clear. So what will be happening? From here I will get some equation 1. Okay, and from right side, from this second also I have another equation 2. Now this dx component will be variable, however q in both 1 and 2 will be same. Okay, so if q in both 1 and 2 will be same, then we can equate these equations 1 and 2 in order to find out finally my value of x equal to 47 centimeter. Is this point clear or any confusion? Do I repeat this point or is this clear?
Clear, sir.
Okay, so basically q will be same, but dx we are integrating, so that's why our dx value we can take it on the right hand side and we can equate. Okay, so this is with this I think all our questions are over, and I expect that I think I have covered in the questions all the topics which you have learned till lecture 8, and from lecture 8 onwards I think you are going to cylindrical and spherical coordinate system, so probably that we will be covering in the next tutorial session. Okay. So now I will first stop the recording, and then we can discuss about the date of the quiz as well.
Sir, can you please share the